On the evening of September 26, 2022, a room full of scientists at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, erupted in cheers at the exact moment their screen went black. No signal, no image, no telemetry, just static. In any other context, the loss of a $325 million spacecraft would be a catastrophe. On this night, it was the objective. The spacecraft had just slammed into a rock floating 6.8 million miles from Earth at roughly 14,000 miles per hour, and the moment of its destruction was the moment of its success. It was the first time in the recorded history of our species that humanity had deliberately altered the trajectory of a celestial body. And the reason they did it, the reason an entire space agency spent years and hundreds of millions of dollars building a machine whose sole purpose was to be annihilated on impact, begins with a rock that hit this planet 66 million years ago and ended 75% of all life on Earth. What happened that night in Maryland was not a science experiment. It was a rehearsal for the survival of civilization. And if you do not know the details of how it worked, you do not understand how close the margin actually is. But before you can understand what they crashed into that rock, you need to understand what a rock can do to a planet. 66 million years ago, an asteroid approximately 6 miles wide struck what is now the Yucatan Peninsula in Mexico at a speed exceeding 40,000 miles per hour. The impact released energy equivalent to roughly 100 trillion tons of explosive force, more than 1 billion times the energy of the atomic bomb dropped on Hiroshima. It punched a crater 120 miles across and nearly 19 miles deep. The collision vaporized thousands of cubic miles of rock, sent a wall of superheated air racing across the continent at hundreds of miles per hour, and launched so much dust and sulfur into the stratosphere that sunlight was blocked globally for months, possibly years. Temperatures plummeted. Photosynthesis collapsed. The food chain disintegrated from the bottom up. Roughly 75% of all species on Earth went extinct, including every dinosaur that did not evolve into a bird. An entire biological dynasty, 170 million years of dominance, was erased in what may have been a matter of months. The event is known as the Chicxulub impact, named after a small town near the crater site, and it remains the most catastrophic single event in the biological history of this planet. That asteroid was not unusual. It was simply large and unlucky in its trajectory. There are millions of objects in the solar system whose orbits bring them close to Earth. NASA has identified over 27,000 near-Earth asteroids as of 2022. Roughly 10,000 of them are large enough to cause regional or global devastation if they struck the planet. Finding these objects before they find us is the single purpose of the agency's Planetary Defense Coordination Office. A real office with a real budget and a real mandate. Now here is the problem that should keep you watching. Finding an asteroid is one thing, stopping it is another. And until September 26, 2022, humanity had never tested a single method of deflecting an asteroid in real space against a real target under real conditions. Every plan existed only on paper. Every simulation was theoretical. Every assumption was untested. The Double Asteroid Redirection Test was designed to change that. The target was not a rogue asteroid headed for Earth. The mission planners chose something safer and more scientifically useful, a binary asteroid system called Dimorphos, from the Greek word for twin. Dimorphos is the larger body, roughly half a mile across. Orbiting it is a smaller moonlet called Dimorphos, approximately 525 feet in diameter, roughly the size of a football stadium. Dimorphos completed one orbit around Didymos every 11 hours and 55 minutes. The system posed no threat to Earth whatsoever. It was chosen precisely because it was safe, observable from ground-based telescopes, and its orbital period could be measured with extraordinary precision before and after impact. The spacecraft itself was remarkably modest for such an ambitious mission. It was roughly the size of a vending machine, weighing 1,260 pounds at the time of impact. It carried no warhead, no explosive charge, no weapon of any kind. Its only instrument of destruction was its own mass and its own velocity. The concept is called kinetic impact, and it is the simplest idea in physics. If you throw something heavy at something else fast enough, the thing you hit will move. The question was whether a spacecraft the size of a vending machine, hitting a rock the size of a football stadium at 14,000 miles per hour, would produce a measurable change in that rock's orbit. The spacecraft launched on November 24, 2021, from Vandenberg Space Force Base in California, aboard a Falcon 9 rocket. It then traveled for 10 months across nearly 7 million miles of interplanetary space. For most of that journey, the spacecraft was essentially a projectile, making minor course corrections using its onboard ion propulsion system. But the final 4 hours were entirely different. During the terminal approach phase, the spacecraft switched to autonomous navigation using an onboard camera system called the Didymos Reconnaissance and Asteroid Camera for optical navigation. This camera identified Dimorphos against the star field of deep space, distinguished it from the larger Didymos, and guided the spacecraft to a head-on collision without any human input. The light delay between Earth and the spacecraft at the moment of impact was approximately 38 seconds. No human could steer in real time at 14,000 miles per hour with a 38-second communication lag. The spacecraft had to find the asteroid and hit it on its own. If you are starting to grasp the precision required here, subscribe, because the results exceeded every prediction. The last image transmitted by the spacecraft was captured approximately 1 second before impact. It showed the surface of Dimorphos in extraordinary detail, a field of boulders and rubble illuminated by sunlight, growing larger in the frame until the signal terminated. The spacecraft struck Dimorphos at 7:14 in the evening, Eastern Time. The impact generated approximately 3 tons of explosive force equivalent, not from any warhead, but purely from the kinetic energy of a half-ton machine moving at 4 miles per second. A companion satellite provided by the Italian Space Agency, released from the spacecraft 10 days before impact, photographed the collision from a safe distance. The images showed a brilliant plume of debris erupting from the surface of Dimorphos. Thousands of tons of asteroidal rock blasted into space by the force of impact. This debris plume was critical. The ejected material acted like a jet of exhaust, pushing Dimorphos in the opposite direction and amplifying the momentum transfer far beyond what the spacecraft's mass alone could have achieved. Scientists call this the momentum enhancement factor, and it turned out to be significantly larger than predicted. The results, confirmed by weeks of ground-based telescope observations, were staggering. The minimum benchmark for mission success had been defined as a change of 73 seconds in the orbital period of Dimorphos. 73 seconds. Just over a minute. That was the threshold the National Aeronautics and Space Administration considered sufficient to declare the technology viable. The actual change was 32 minutes. The impact shortened the orbit of Dimorphos from 11 hours and 55 minutes to 11 hours and 23 minutes. The mission exceeded its minimum success threshold by more than 25 times. A spacecraft the size of a vending machine, carrying no explosives, relying on nothing but velocity and mass, had permanently altered the orbit of an asteroid and reshaped its entire structure from a symmetrical sphere into an oblong form resembling a watermelon. The rock was not just nudged, it was deformed. Think about the implications. In a real planetary defense scenario, the deflection required to save Earth from an incoming asteroid depends on two factors: the size of the push and the amount of warning time. A change of 32 minutes in orbital period, applied to an asteroid years or decades before a projected impact, could translate into a missed distance of thousands of miles. The difference between extinction and survival might not require a nuclear weapon or a science fiction laser. It might require a box the size of a vending machine, launched early enough, aimed precisely enough, and traveling fast enough. The mission also revealed something unexpected about Dimorphos itself. The asteroid was not a solid monolithic rock. It was what scientists call a rubble pile, a loose aggregate of boulders and dust held together by weak gravitational cohesion rather than structural strength. This matters enormously for future planetary defense, because the effectiveness of kinetic impact depends on what the target is made of. A rubble pile absorbs and redistributes energy differently than an iron-nickel body. The data from this mission will inform every future deflection calculation for every asteroid that is ever identified as a potential threat to Earth. The European Space Agency launched a follow-up mission called Hera in October 2024, scheduled to arrive at the Dimorphos system in 2026. Hera will conduct detailed surveys of the crater left by the impact, measure the precise mass of Dimorphos, and assess the long-term effects of the collision on the binary system. The data from both missions combined will constitute the most comprehensive understanding of asteroid deflection physics ever assembled. The total cost of the mission was $325 million. For context, that is roughly the budget of a single Hollywood blockbuster film about asteroids destroying the Earth. It is less than 0.1% of the annual United States defense budget. It is less than what Americans spend on Halloween candy in a single year. It is, by any rational accounting, the cheapest insurance policy ever purchased by a civilization that knows, with mathematical certainty, that another large asteroid will eventually cross its path. 66 million years ago, a rock 6 miles wide ended the age of the dinosaurs because nothing on this planet could stop it. Nothing could see it coming. Nothing could push it out of the way. The dominant species on Earth, creatures that had ruled every continent for over 170 million years, were erased because the universe does not issue warnings and nature does not negotiate. On a Monday evening in September of 2022, a room full of human beings in Maryland watched a screen go black and cheered, because for the first time in the 4.5 billion year history of this planet, something living on its surface had reached out across 7 million miles of empty space and moved a rock. Not because it was falling toward us, but because someday one will.